Okay, so we have seen how to represent predicates in type theory, but the interesting thing about predicate logic is that we have quantifiers for all and exists for quantifying overall predicates. So either saying that something holds for everything or that there is something that makes something true. So let's see how we do these things in type theory. So the first thing we have to answer is, what is a proof of, let's start with universal quantification. So what is a proof of for all x in A, P of x? And if you think about it, this should be something which, if you give it any A in A, then it gives you back a proof of P of A. Right? So it's really a proof of P of A for every A. Okay, but what is this? But a dependent function. It's a bit big. So we can just identify the universal quantification with the dependent function space that we've seen before, where we have this functions from A into P, where the type of the codomain of the function depends on the element that you feed it. So let's do an example, which is this thing, which says that for every n, which is a natural number, either n is even or suc of n is even. Right. Okay, so how do we prove this? Well, it's just a function, so we just write a program which has the right type. So because it's a function, we give it an argument, call it n, we reload, and now in order to make progress, if you look at how is even was defined, it was defined by the pattern matching on the argument you give it, right? So in order to reduce this, we need to know what n is, so we also pattern match on the n. It's stuck because we don't know what the n is yet. Okay, so if the n is 0, then this says is even 0 or is even 1. And if we look at the definition of is even, we see that is even 0 should evaluate to true. So if we look at what we have to prove here, we see that we either have to prove true or false. Well, it seems much easier to prove true, so let's do that. That's the first injection of something, and then this something should be something in the unit type, which is our favorite constructor TT. Okay, what about here? So here we have to say that either suc of n is even or suc of n is even. Okay, we don't know which one of this is it yet because we don't know what n is, so we have to pattern match on n again. Okay, so now we have 1, so now we have to prove that either 1 is even or 2 is even. And if we normalize this, we see that this reduces to either proving false or proving true. So this time we should do the second injection of our favorite constructor. Okay, and finally here then, we have to show that either suc n is even or suc n is even. But if we reduce this as much as possible, we see that suc n is even of suc n is going to reduce to is even of n. So this just reduces proving the same thing again for n, which means that we can do a recursive call and prove that. And this is fine because n is smaller than suc n, so it's going to terminate eventually. Right. So that's a typical proof of something of a universal statement. Just write a function and do the appropriate pattern matching to make it go through. And then we see that A implies B is just the same thing as a spurious universal quantification where we're not using the argument. Right? So we see this identification of implication and universal quantification in this logic, which is kind of neat. Okay, so what about existential quantification? What is a proof of there exists an x such that P of x? Well, if you think about it, such a proof should be a particular A in A together with a proof that P of A holds. Right? So you choose a witness and then you prove that it really is a witness, which means that this is nothing but a dependent tuple. And it's dependent because the type of the second component of the tuple depends on the first element, right, which is exactly this so-called sigma type. You can go and look in the library, and we see that the sigma type is defined like this. So you give it an A and you give it a B, which is a predicate over A. It has a constructor, which is this pairing constructor. And to give a sigma type is to give all of its fields. So first, you have to give the first part of the tuple, which is an element of A, and then you have to give the second part, which is an element of B of first. Okay, so let's look at an example. So this is some nicer syntax for the same thing. So you can write it in a pointful style where you have the x, you name the x here so you can use it in the rest of it. Okay, so here's an example. Let's prove that there exists a natural number which is even. Okay, so what do we have to do? Well, we have to give something in the sigma type, and the canonical way to construct something in this type of pairs is to say that it's something paired up with something. Okay, so now we have these two goals. So we say that here we have to give a natural number, and here we have to give a proof that whatever we give, it is even. Right, so here we give our favorite even natural number. Obviously it's 2, well, or whatever you want. And then here we now have to give a proof that is even of 2, which just reduces to true again. So we can just give TT, for example. And similarly we could give 4 or 6. But if we try to give 5, then we see that Agda complains that this is not a proof that 5 is an even number. Because what Agda expects in this case is something in the empty type. So that's not a good example. Okay, so let's look at one more example where we combine forall and exists. I'm calling this carry and uncarry. So this one says that if you have this statement, so you have that exists x in a, p of x implies q, that's the same thing as saying for all x in a, p of x implies q. So you could, seeing it this way, you're exchanging an exists in the hypothesis of a function with a for all outside the whole thing. Okay, so let's see if we can prove this. Okay, right, so first we take an f, that's our assumption, and then we also have to take an a, and we have to take a p, and now we have to produce a q. So we see that we have an f of this type, we have an a, and we have a p. So we see that f will give us a q if we give it something. What should we give it? We should give it something of sigma type, so that's something comma something. Okay, I don't know why that didn't work. Let's do it by hand. Okay, and here we have to give an a, but we do have an a. And here we have to give a p of a, but we have a p of a. Right, so we take the a and p separately and we give them as a pair to f. Okay, what about this one? So here we have given a g and some r, say. And what we have g, which is this function, and we have r, which is of the sigma type, so we can pattern match on the r. See that it must be of the form a comma p. Okay, and now we have to give a q again. G will give us a q if only we give it two things. What are these things? Here we have to give it an a, we have an a. Here we have to give a p of a, we have a p of a. Right. So what we see here is that you might recognize these two functions as the standard functions carry and uncarry, say from the Haskell prelude, except that they are working with these fancier types now. Right? So they're not just about pairing and unpairing, they're really about exist and for all. But it turns out that it's the same underlying proof, or the same underlying program that does the same thing for predicate logic and for propositional logic. And and here's another nice thing, that the ordinary pair A times B you can just realize as a dependent pair where the second component doesn't actually depend on the first thing. Right? So you see that just like we unified implication and for all, here we're also unifying conjunction and exists. Right? So you see that these are really the same kind of thing in type theory.